Hello friends, in this video we are going to learn about nuclear binding energy and mass defect. Okay, so two particular concepts we'll discuss. One is mass defect. We'll discuss mass defect first and then we'll discuss nuclear binding energy. So what are these two concepts? So we all know that a nucleus, okay, the nucleus of an atom is basically made up of protons and neutrons. Okay, so in a nucleus there are protons and neutrons. So what is our expectation from this? Our expectation from this, okay, if we write expectation, our expectation from this would be that the mass of a nucleus, if I write MNUC, mass of a nucleus, that is equal to the mass of protons plus the mass of neutrons. Okay, this should be our expectation in such a case. But the question is, does this really happen? Is this true? Since protons and neutrons make up the nucleus, so will nuclear mass is nuclear the nuclear mass equal to the summation of the masses of protons and neutrons? So actually this is not true. Experimentally it has been found that the mass of a nucleus, okay, mass of a nucleus is actually less than the summation of the masses of the protons and neutrons. That means the nuclear mass is always less than the summation of the individual masses of the protons and neutrons. So if you calculate the masses of protons and neutrons in a nucleus and compare that with nuclear mass, you will always find a difference in mass. So that mass is known as mass defect. Okay, mass is known as mass defect. Okay. So mass defect basically is, let me write it again. So mp plus mn minus m nuclear. Okay, the nuclear mass. So this is basically the mass defect, which is generally sometimes referred to as delta m. Suppose, okay, delta m, which is the mass defect. Okay, so I hope by now you have understood what is the concept of mass defect. Okay, mass defect is simply the mass difference which is obtained if we add up the masses of individual protons and neutrons in a nucleus and compare that with the mass of the nucleus itself. Okay, so that concept is the mass defect. Now again, another question is, what is the nuclear binding energy? Okay, in order to understand the concept of nuclear binding energy, so let us come back to mass defect again. So as per Einstein, or as per Einstein's equivalence of mass and energy. So what is Einstein's equivalence of Einstein's equivalence? Einstein's equivalence of mass and energy. Okay, mass and energy. As per Einstein's equivalence of mass and energy, so mass can be converted to energy, and conversely energy can be converted into mass. Okay, so this is basically Einstein's equivalence of mass and energy. So if mass defect is delta m, okay, delta m is the mass defect, so then what will be the energy equivalence of this delta m? In order to calculate the energy equivalence of this mass difference, we have to multiply delta m by c square. Okay, so where c is the speed of light. Okay, c is the speed of light. So again, in this case, this delta mc square is basically the nuclear binding energy. Okay, so that is how, from the concept of mass defect, we can understand the concept of, we can get the value of nuclear binding energy, For that, we can cite Einstein's mass energy equivalence relation. So again, if I now ask you, how would you define nuclear binding energy? Okay, so nuclear binding energy can be defined as how much energy will you have to supply to break a nucleus. Okay, how much energy you will have to supply to break a nucleus into constituent protons and neutrons again. Okay, so how much energy you will have to apply to this nucleus to break it into protons and neutrons. Okay, already we have seen that protons and neutrons constitute a nucleus. So that is the nuclear binding energy. And then again, how much energy you'll have to supply, that is the nuclear binding energy, and this much energy you have to supply, okay, which is numerically delta m multiplied by c square. Okay, that is the expression for energy. So yes, basically that is the nuclear binding energy. Or simply, if we have to separate a nucleus into its constituents, so how much energy is required? That is the nuclear binding energy. Okay, nuclear binding energy is generally represented by this like sub EB. Okay, EB, nuclear binding energy. Okay. So there is another concept called binding energy per nucleon. Okay, so in order to express nuclear binding energy, so there is another concept which we will learn in the next video class. So that is called binding energy per nucleon. Binding energy per nucleon, which is EB over A. Okay, A is the uh, total number of protons and neutrons. Okay, A is simply total number of protons and neutrons. Okay, so now to give you a rough idea of how much is the binding energy of, suppose, a nitrogen nucleus. Okay, nitrogen 14(7). What is the let me write it in another way. What is the nuclear binding energy of this nucleus nitrogen? So as you can see, it's uh, A is equal to 14. Okay, and number of protons is it has 7 protons and it has got 7 neutrons. So I'll not go into the details of the calculation. You have to consider the mass of each proton, you have to consider the mass of each neutron, something like this: 7 multiplied by mass of all the protons, 7 multiplied by the mass of all the neutrons, minus the mass of this what is the mass of nitrogen 14, that you have to subtract. You will get some difference in mass, and if you use this formula delta mc square, if you calculate the nuclear binding energy, we will find that the nuclear binding energy of nitrogen 14 is almost equal to 105 mega electron volt, almost equal to 105 mega electron volt. So what does that mean in this case? In this case means it means you have to supply, I mean, in order to break nitrogen into its constituent 7 protons and 7 neutrons, you will have to supply this much amount of energy. Okay, which is quite high. This is a very high amount of energy. But again, how this energy is possible? This energy again becomes possible because of this mass defect, and if we consider Einstein's mass energy equivalence relation. Okay, so similarly for other nucleus also, like suppose oxygen 16, also you can calculate the nuclear binding energy if you know the masses of protons and neutrons of oxygen and the oxygen nuclear mass. So you can also calculate the nuclear binding energy. So therefore in this video I have given you some idea of this some idea of mass defect and nuclear binding energy. What is mass defect and how you can and how is it related to nuclear binding energy? What is nuclear binding energy? And also this example of nitrogen 14, although I have given you just the value of nuclear binding energy when a nitrogen 14 nucleus has to be broken into the constituent protons and neutrons. Okay, so in the next video we'll learn about this concept binding energy per nucleon. So there will be a graph which we'll be discussing. So friends, thank you very much for watching, and I will see you in the next video. So thank you very much.